Roll number 1, Shakib.
Present, sir.
Roll number 2, Arindam.
Present, sir.
Roll number 3, Tisha.
Present, sir.
Roll number 4, Monojit.
Present, sir.
Okay. Roll number 5, Mayuk.
Present, sir.
Roll number 6, Abhrodip.
Present, sir. Present, sir.
Okay. Roll number 7, Gunjan. Gunjan.
Present, sir. Present, sir.
Okay. Roll number
Present, sir.
roll number 8, Shivam Chatterjee.
Present, sir.
Roll number 9, Shagnik. Roll number 9, Shagnik. Roll number 10, Shivshankar Das.
Present, sir.
Roll number 11, Indira.
Present, sir.
Roll number 12, Aloy.
Present, sir.
Roll number 13, Moyuk.
Present, sir.
Roll number 14, Riju.
Present, sir.
Roll number,
Present,
roll number 15, Shubhojit.
Present, sir. Present, sir.
Roll number 16, Shaurish.
Present, sir.
Roll number 17, Junaid.
Present, sir.
Roll number 18, Upasana.
Present, sir.
Roll number 19, Shidipta.
Present,
19.
sir. Present, sir.
Okay. 20, Ritu Kole. Ritu.
Present, sir. Present, sir.
21, Dharam. Dharam Kumar.
Present, sir. Present, sir.
Okay. Roll number 22, Saurabh Kumar Maiti. Saurabh Kumar Maiti.
Present, sir.
Roll number 23, Shayan Mullik.
Present, sir. Present, sir.
Okay. 24, Shinjana.
Present,
Shinjana.
Sir, roll number 22. Present, sir.
I have already given it. Roll number 25, Anurag.
Present, sir. Present, sir.
Okay. 26, Chandima.
Present, sir.
27, Shayan.
Present, sir. Present, sir.
Okay. 28, Devjit.
Present, sir.
29, Sambuddha.
Present, sir.
30,
Present, sir.
30,
Present, sir.
Sosha.
Present, sir.
31, Shubhajit.
Present, sir.
32, Sharbani.
Present, sir. Present, sir.
33, Rajkumar. Rajkumar. 33, Rajkumar. 34, Songrag.
Present, sir.
35, Farjan Reza. 35, Farjan Reza. 36, Shubhashish. 36, Shubhashish.
Present, sir. Present, sir.
37, Shayan Kumar.
Present, sir.
38, Shayan Sarkar.
Present, sir.
Okay. 39, Parthik Sharma.
Present, sir.
40, Shivashish Kumar. Shivashish Kumar Sengupta.
Present, sir.
41, Chetan Singh. 41, Chetan Singh. 42, Madhusudan Yadav.
Present, sir.
Hello, sir. 41 Chetan Singh, sir. Present.
Okay.
Hello.
Now, yes, I have already given.
Okay, sir. Thank you.
So let us begin where we left actually under Christoffel theory also, and we are going to share the screen. Okay, just a minute. Just a minute. Hello, any screen is visible?
Yes, sir.
Hello.
Yes,
Yes, sir.
sir. Yes,
Yes,
sir.
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 Okay,
Yes,
very
sir.
good.
Visible spectrum.
Okay, very good. If you remember, in continuation of under crystal field theory, what we tried to explain that in case of the octahedral complexes, what splitting of degeneracy in terms of the splitting of the degeneracy of the d atomic orbital takes place in the opposite manner. The degeneracy breaking takes place in case of crystal field means in case of tetrahedral complexes. Okay, so these are the example actually. If you find that the orbital energy level diagram octahedral complexes or so, here you are finding in case of D10 electronic configuration, as you understand very well, that here in terms of triply degenerate dxy, dyz, dzx, and at the same time dx square minus y square and dz square, all are completely filled up and the pair. Okay. Now, let us understand the colors of transition metal complexes. First of all, I would like to remind you, you know it very well. Generally, it is possible due to presence of actually unpaired electrons. Mostly, you will find that this is in particular, which is related to the transition metals, where you will find due to availability of unpaired electrons or so, they show the color behavior as well as the paramagnetic nature. Okay, as you know it very well. And now, in continuation of that, if you see the visible spectrum, then you know that is in terms of the range is 400 nanometer to 700 nanometer. That means 4,000 angstrom to 7,000 angstrom. You can understand that from left to right, as you see, the wavelength increases. That means from violet to red. So naturally, it is going to be lower energy and higher wavelength. In terms of, you know that Planck's quantum theory, that is E equal to h nu and E equal to h into c by lambda. So therefore, energy is inversely proportional to wavelength, and whereas the energy is directly proportional to the frequency. And as far as the white, all the colors wavelength. Basically, I would like to remind you, all of you know it very well, that as far as whenever you find any object, basically any object cannot be just like as such any color. What we find the light reflection from that point of view, we can observe what will be its possible color if it is in the visible range. For example, I'm saying, suppose if you find that any body is white in color, you are finding, suppose, that means whatever the photon actually incident upon this, all are going to be reflected back. Nothing is going to be absorbed by that object. On the other hand, suppose if you come across that any object is black in color, so that means whatever the photons or that means it is being incident upon that object, black body object, it absorbs all the radiation. So nothing reflects back. So that's why nothing almost reflects back. That's why we are observing it is black in color. And on the other hand, sometimes whenever you are observing any object is having some color, that means some part of the white light, as you know that it is polychromatic in nature, is being absorbed by the object, and some part is going to be reflected back. And accordingly, you are viewing that color. If it is in the range, then you will find the complementary color also. So I'm going to explain that one. Okay, look at here. Suppose colors of transition metal complexes. So you will find the absorption of UV visible radiation by atom, ion, or molecule. That means ultraviolet visible range. Okay. Why we are saying? Because you know the violet actually 400 nanometer it begins naturally. So ultraviolet visible range we are saying. Okay. Now occurs only if radiation has the energy needed to raise an electron, as what we understand, from its ground state to an excited state. That is from lower to higher energy orbital. So mostly you can generally sometimes you explain the DD transition. That means suppose from triply degenerate to doubly degenerate, the jumping of the electrons or something like that. So light energy absorbed equal to energy difference between the ground state and the excited state. That means electron jumping. We are saying. Now look at this colored disk. Actually, you know the Newton's colored disk or so. What happens? You will find that is the, for example, if the any object absorb this energy of this color or wavelength orange, then we will see the observed color is blue of that object. Okay. Similarly, if it absorb, for example, that the blue color, then we will see that object as an orange color. In this way, suppose if an object actually you are finding that it absorbs the yellow length wavelength actually of white light, then we will see that it is going to be violet in color and vice versa. So in this way, you can find the complementary. If orange is absorbed, we will see blue color. If blue is absorbed, we will see it orange color. Similarly, if yellow is absorbed, then we will see violet color, and if violet is absorbed, then we will see yellow color. Similarly, if green is absorbed, we will see red color, and if red is absorbed by that object, then we will see it's green in color also. Okay, like that. Whether up to this, it is understandable? Any question?
Yes, sir. মানে অপোজিটের কালারটা সোয়াপ করবে।
হ্যাঁ, right, exactly. So this you know it already very well. Okay.
Complementary color theory.
Yes, exactly, complementary. Right, absolutely right. You just see that. Right. You just see the colors of transition metal complexes. For example, what I am showing here. You are finding that 1, 2, 3. Okay. So the white light, suppose red light absorbed. For example, I am saying, and then what you will observe? It is a green light. Are you getting my point? Have you understood what I'm
Yes, sir. Yes, sir.
What I'm saying?
No,
Suppose white light incident upon any object, for example, and if the object actually absorb the wavelength of the red light range, actually, then you will see that object in green in color. That is the complement.
Okay.
Look at here. Look at here. Suppose if it is red, then opposite is what? Green. Okay, and the vice versa. If it absorbs the green color from the white light by that object, then we will see red. Okay, like that.
Okay, sir.
So here you are finding the for transition metal complexes, that is the energy splitting. You are finding the energy difference correspond to energy of the visible light, and here you find finding the absorption raises an electron from the lower d subcell to the higher d subcell. Look at here. 1, 2, 3. Okay, for example, so now here actually 1, 2, 3, 4, 5. Now from here you are finding one electron jumps to the higher energy level. Are you getting my point? Like that, you will see.
Yes, sir.
Just see here. So colors of transition metal complexes, you will find that different complexes exhibit different colors because color of the light absorbed depends on actually crystal field splitting. Larger the splitting, higher energy light absorb. That means shorter wavelength absorb. So therefore, you will see actually that is a shorter wavelength. What I'm saying, that if you see the suppose shorter wavelength, for example, if it is going to be violet, then if it is violet being absorbed, then you will see the yellow in color like that. Okay, and similarly, if you find this, for example, just a minute. Similarly, suppose smaller splitting, that means the equal to lower energy light absorb. What's the smaller splitting? You are finding in terms of breaking of degeneration of d atomic orbital. That means between triply degenerate and the doubly degenerate. Okay, in case of the suppose octahedral complexes we are explaining, for example, what I am saying. So then when you are finding the larger del, that means higher energy light absorb, that means shorter wavelength. And when you are finding the crystal field splitting is less, for example, smaller, then it is lower energy light absorb, so longer wavelength. And then you know already the magnitude of this crystal field splitting depends upon so many factors. Already we have studied it well, in terms of from the spectrochemical series, the strong ligand, weak ligand, then the nature of the metal, etc. Okay. And look at here. For example, Whether it is visible? Hello?
Yes, sir.
Okay. You just see here MEN whole 3 plus. You understand this basically that this is actually tris ethylene diamine, or you can say tris ethene 1 2 actually diamine. Okay, the metal ion actually, and the oxidation state is Roman 3. For example, now in the aqueous medium actually, for example, the if the of this chelate complexes like this, because you know the in this case the metal atom M actually oxidation state is 3 plus for its, and here it is having the coordination number is 6 because it is forming chelate complexes, chelate complex with 3 bidentate similar En, that means ethylene diamine chelate ligand. So therefore, suppose if white light passes through it, for example, then you are finding the blue light absorb. Blue light absorb means higher energy level. Okay, and here you are finding the orange light actually we will observe. If blue light is absorbed, then what we will see, the orange light we will actually observe. Why? Look at here. What is the complementary? For example, look at here. If you see the blue color, the opposite is what? Orange. And vice versa. If it absorbs orange color, we will observe the blue color like that. Hello, this is understandable what we are saying.
Yes, sir. Yes, sir.
Yes,
Okay,
sir.
good.
Yes, sir. Understandable.
Oh, okay. Look at here. For example, we have taken some example. Suppose the energy splitting, okay, the between triply degenerate and the doubly degenerate, okay. The here at the bottom you are finding the triply degenerate dxy, dyz, dzx, and at the top you are finding the doubly degenerate dx square minus y square and dz square. And look at here. Suppose here F63 minus. Here, if you look at the oxidation state of chromium, here +3. And what's the coordination number? 6. Okay. And here, in case of the next one, you are finding chromium H2O whole 6, 3 plus. Okay. So you are finding it is generally violet in color. Here also, you are finding oxidation number of chromium is +3 and the coordination number is 6. The next one, you are finding that hexamine chromium 3 ion actually. So you are finding here also the same actually, the oxidation state and coordination number. The next one also you are finding the same, but you just see different in color. Okay, with depending upon the ligand, because here you are finding the same metal ion in the same metal atom in the same oxidation state, the +3. But here you are finding for CrF6 3 minus the green color in the aqueous medium, you are finding this is suppose violet color, this is yellow color, and the next one also nearly you are finding yellow color. Why? Because you know that if you look at this actually, you know that generally in terms of increasing order of strong ligand, you find from the spectrochemical series, from fluoride to the aqua, from aqua to ammonia, from aqua to actually cyanide. So naturally, accordingly, you look at here, what's the splitting here in terms of del energy difference. In the next one, you are finding the energy difference is a little bit increasing. Then in case the next one, it is little bit further increasing, and in the next one, you are finding that it is further splitting. That means further del is actually increasing. So in this case, if you look at here, if why it is yellow color, because somewhat here it is going to, with the cyanide ligand, it is going to absorb the energy of shorter wavelength. Okay, so suppose if we look at the complementary color, for example, you look at here for yellow, that means almost blue color it is absorbing. So that's why you are finding the as far as just a minute. That's why you are finding as far as CrCN whole 6 3 minus is concerned, that is you are finding yellow color, nearly the same as the ammonia, because here crystal field splitting is very high. Or on the other hand, as you understand, here the crystal field splitting is actually less, so naturally it requires actually less energy of longer wavelength. So that's why the color is going to be what you are observing, the complementary color of shorter wavelength. Okay. Like this, we generally observe why we find the different types of color in the complexes also. Hello, it is up to this, it is understandable. If you have any question, you can ask me in this regard. If you require further explanation about this. Why? Because that means depending upon the splitting, you can find the electron, the when it may jump from lower to higher. Now, with respect to the other condition remains same in terms of the metal atom and the oxidation state, you are finding that only it differs with respect to the ligand, because in spectrochemical series, if you come across, you can find from left to right, that is the increasing order of strong field ligand. So accordingly, you are finding they are going to absorb the energy, means white light, where you can find the energy of higher energy of shorter wavelength. So accordingly, you will observe the complementary color of longer wavelength also, like that. Okay.
Sir, then with this chromium F6, this one and the next one. So the first one is getting the lesser energy difference. So
Yeah.
that will have the means longer wavelength.
Actually, you try to understand lesser energy means actually you are finding the longer wavelength. Okay, isn't it?
Yes, but green is not among one of the longer wavelength ones.
Just try to understand. Green, actually you are seeing that complementary color, opposite, a shorter wavelength.
Oh, okay, means red. So red will come as opposite one for green.
Yes, right. Actually, here you are finding the when you are seeing this is a green color, basically you just see, you expect that it is absorbing the red actually, because it is a longer wavelength,
Yes.
low energy splitting. Okay.
Yes,
Okay,
sir.
sir.
The color of the complexes can come in the exam. Means we have to remember which color the complex has.
Exactly, right. Generally, more or less, you can say that sometimes it may not be there exactly, but nevertheless, you can understand the trend. Okay, like this.
Like lesser the difference, we will write on something on green and means complementary of red and orange,
Right,
something like that.
Exactly, absolutely right.
Sir,
Okay, suppose. Hmm,
excuse me.
hmm.
Sir, for example, here green is written. If we didn't know, means if this green word is not written, we would not have understood that this complex has actually green.
Yeah. You have to know this. Why it is? That's why the question. Why the color of this complex is green? Why the color of this complex is violet? Why the color of this complex is yellow? Like that.
We have to explain that, not we have to.
Yes. Because suppose another example I'm showing. Suppose look at here. It is visible the color of transition metal complexes.
Yes.
Yes, sir.
Look at yeah. Hello.
Sir, you're
Hello.
audible.
Okay.
You're
Look at
audible.
here. You just see the color of transition metal complexes. You are finding the variety of color among transition metal complexes has long fascinated the chemist. For example, aqueous solution, you are finding the hexa aqua, okay, iron 3 plus ion actually, are red, and whereas you are finding hexa aqua cobalt 2 plus ion are pink. Why this? Suppose nickel hexa aqua are green, are these are hexa aqua copper. You already know the copper sulfate solution, for example, green, because the copper is actually going to be hydrated with like that in the aqueous medium. Similarly, whereas you are finding zinc ZnH2 whole 6 2 plus are colorless. Why? Because you know in case of the Zn actually 2 plus mean that from 4s there will be removal of the 2 electron, and in case of the Zn3d all the 5 atomic orbitals going to have 2 electrons each pair. So naturally, there will be no question of any electron transition, no unpaired electron. So that's why you can find basically the here you are finding the colorless. Okay, and whereas in case of the CuH2 whole 6 2 plus, you are finding blue. So So that means you can expect as generally H2O is a weak field ligand, so therefore the crystal field splitting is not so high in this case, and therefore you are finding it is absorbing of longer wavelength, okay, the or higher longer wavelength and the less energy is required for splitting. So that's why you are finding the observed color is blue of higher energy of shorter wavelength. Similarly, in case of nickel hexaqua H2O, you are finding green, okay, because that means the hair splitting is due to most probably in the range of the red type means energy of this sort of the wavelength also, like this. That you can understand, because what I explain actually, the what we see color once again, the when a sample absorb light, when, what we see is the sum of remaining color that strikes our eyes, okay, and if a sample absorb all the wavelength of visible light, none reaches our eyes from the sample, and then the sample appears black, what we have already explained. And similarly, if the sample absorb no visible light, that means everything reflects, it is white or colorless, okay, already we have discussed. Now when the sample absorb a photon of visible light, it is its complementary color we actually see. For example, if the sample absorb orange color, it would appear blue, and if it blue and orange are said to be complementary color. So that's why this is the color wheel. For example, the color of the light absorbed, whether it is visible. Hello.
Yes, sir.
Okay, look at here. The red light you are finding
Yes, sir.
the it is 700 to 620 nanometer range. Okay, so color of the light actually transmitted green, because you just see the red, the complementary color is green. Suppose here the left hand side column, we have shown for what color of the light is being absorbed, and by that substance, any substance. Suppose not only the complexes, by any other substance normally. And in the right one, you are finding the color of light transmitted. Then if it orange is absorbed, you just see the complementary color. You will find the blue color is transmitted, and that you actually find. And then if yellow color, then you are finding complementary is violet. Then if it is green color, you are finding complementary red. Then if it is blue color, the complementary is orange, okay, like that. Or if it is violet, then yellow, okay. So you
Use
are
examples in order to predict the colors.
yeah, look at here, for example, here just to make you understandable, just a minute, the color of coordination complexes, you know, what I try to explain in here we have taken the example of basically the octahedral complex splitting. So you already know the T2G, this is triply degenerate, and the EGW degenerate. Suppose the left hand side you are finding here the oxidation state of the V is 3, for example, the metal atom, okay, and here it is oxidation state 3 plus, and what's its ion? You are finding the D2 electronic configuration. In the second case, you are finding the oxidation state of the same metal atom actually, the +2. So naturally, you are finding in the atomic orbital how many electrons are there? D3. So here you already know, we explain it that with the higher oxidation state, the octahedral splitting is going to be higher. Okay, and whereas if you look at this, the with the oxidation state lower, the crystal field splitting is going to be small. Okay, and here you are observing two different color. Suppose here you are finding almost yellow color. Here you are finding right hand side violet color. Okay, is it clear what I try to explain?
Yes, sir.
So that means we are here left hand side you are finding
Yes,
the
sir.
violet light absorb complex appears yellow, and on the other hand the right hand side suppose the yellow light absorb complex appears violet. Clear?
Yes,
Yes,
sir.
sir.
Because here the crystal field splitting is less, and you already know that with the for the same metal atom with the higher oxidation state crystal field splitting is higher. And suppose here what is happening, just to make you understandable, that violet light absorb, so complex appears yellow, okay, and on the other hand the right hand side the complementary just opposite, yellow light absorb suppose and complex appears violet, like that. So therefore you are finding just you look at here the chromium Na is 3, okay, whole 6 3 plus, And here you are finding the strong octahedral crystal splitting. So high energy you are finding violet light absorbed. So complex is yellow in color. And whereas here it is incidentally, it is going to be the homoleptic actually, that's a similar kind of all monooriented ligand. But on the other hand, the right hand side, if you consider, this is also the octahedral complex, but here you are finding that Cr NH3 whole 5 and Cl, that means it is heteroleptic. But other than 5, you are finding that neutral, actually monodentate ammonia ligand, the one is actually negatively charged chloride ligand. Okay, and overall you are finding it is considering, because of the presence of another chloride ligand, it is having some weak field splitting. And here you find that the low energy yellow light absorb, and therefore the complex is somewhat magenta in color. And here suppose all by blue we are showing this is the ammonia ion, and here all by blue we are showing this is the ammonia, and whereas by green we are showing actually that is actually for chloride ligand also. And the variation of this already we have explained. So therefore, sometimes I try to explain actually in case of this, what is the geometry and the hybridization, etc. In case of appearance, in case of the titanium H2O whole 6 3 plus, though we can say the octahedral complex, but it is not going to be exactly the same octahedral complex actually, means in terms of the symmetry, because the perfectly octahedral should give only one DD transition. However, distortion occurs to eliminate the degeneracy of the system. Okay, if the complex distorts from regular octahedral geometry, the T2G and EG levels are split, the consequence of which in the appearance of the solder as shown in the figure below. Why it is happening? I am telling you. Because look at here, when you are saying the titanium 3 plus, that means you are writing there will be D1 electronic configuration. Okay. Now, so long when dxy, later on we will discuss when we will get the time, that is in terms of John Taylor distortion actually. For octahedral complex, one you will find Z in and another you will find Z out. Z out means you will find that is the Z elongation along the axial bonds, and whereas in case of the Z in, you will find the compression actually, that is the shorter of the axial length with respect to the equatorial length. I will come to that later on. When does it happen? Generally, whenever you are finding, suppose the D1 electronic configuration, then what is happening? That you are finding dxy, dyz, dzx. So in this triply degenerate, suppose for example in the dxy there will be one electron. Then there will be no electron in dyz and dxz. So what is happening? That it is causing some asymmetric behavior. Okay, so because of that, some unsymmetrical is going to be in nature. So that's why to overcome that, actually, you will find to further distortion occurs to eliminate the degeneracy of the system. And because of that, so similarly, suppose when dxy one electron, if dyz one electron is there, then again there will be some sort of asymmetry. But if you see that dxy, dxz and dyz all are going to have one electron each, then somewhat it is not going to be asymmetric, because each atomic orbital is going to be occupied by one electron each. Okay, so therefore you can find that d1, dt, d2 actually some asymmetric. Then again, if you find, for example, if we see the d4, now in case of the d4, and when you are finding no pairing is taking place, generally the one electron goes to doubly degenerate, either dx square minus y square dz square. And normally, whenever we observe the John Taylor distortion, actually, you will find, though we may observe with dxy, dyz, dxz, but it is more dominant actually with the doubly degenerate dx square minus y square or dz square. Okay, with the doubly degenerate. Okay, and now the moment it will have the d5 actually, then the John Taylor distortion you may not expect. So here you are finding somewhat like this. So complexes that contain metal ions of D10 electronic configuration are usually colorless, what we have already explained. Okay, and one would expect a metal complex with no d electron to be colorless as well. However, a few of such complexes are strongly colored. What we explained earlier, the MnO4 minus or Cr2O72 minus, the origin of this color in this complex is not the DD transition, rather due to charge transfer. That means here what is happening, as you are finding the central metal ion, in case of the Mn, that is you are finding +7, the chromium +6, they are having no DD at electrons. So naturally, because of the high charge, actually, they are going to pull the electron cloud towards itself more from the ligands. So therefore, there will be charge transfer actually from ligand to metal ion, and because of that, you are finding that why MnO4 minus is having some bright color, that is the violet pink color, and the Cr2O72 minus, you are finding suppose the orange color like that. Okay, so here you are finding there will be charge transfer from ligand to actually the central metal ion. On the other hand, it is also possible, for example, in case of the nickel carbonyl or the iron carbonyl, because you know here the oxidation state of the nickel and the cobalt, these are the neutral complexes, you are finding the 0. So here what will happen, here there will be the charge transfer actually from basically central metal atom to ligand. That is possible. That is the different aspect. I'm not going to explain right now. So here you are finding the why, how we can observe the different types of color is happening. So therefore, multi-electron system exhibit multiple transition, and the assignment of the absorption band is not straightforward. So the complexity arises due to inter-electron repulsion. That's why you will find so many ambiguities actually. That what you cannot explain all the, in case of all the compound or with the similar type of explanation. Okay. So the complexity arises due to inter-electronic repulsion, and okay, and that we are not going to discuss at this moment. Are you getting my point? Hello? Hello?
Yes, sir.
Hello?
Yes,
Am I
sir.
audible?
Yes, sir.
Yes,
Yes, sir.
Yes, sir.
Okay, good, good. So these molecular vibration, these are not going to explain right now. Okay, very good. Just a minute. These already we have explained like this. Okay, fine. Somehow it is understandable what we have explained right now.
Yes, sir.
Yes, sir.
Okay, good.
Yes, sir.
Okay.
Yes, sir.
Yes, sir. it is
Okay, good, good. Now, what I tried to explain actually, the charge transfer bands actually, the similar to DD transition, charge transfer, you are finding transition also involved in the metal d orbital, and charge transfer bands are observed if the energy of the empty and filled ligands and the metal center orbitals are similar. The direction of the electron transfer is determined by the relative energy level of this orbital, that is ligand to metal charge transfer. Okay, like in manganate ion, chromate ion, then dichromate ion, like this. For MnO4 minus, the d electron count on Mn7 actually, in +7 oxidation state is D0. So the origin of the color in this species is not due to DD transition. Rather, you can find the charge transfer from O2 minus, that the ligand, this is negatively charged, 2 minus to Mn7 plus, described as actually LMCT. That means ligand metal actually charge transfer band. And whereas metal to ligand actually charge transfer, what I try to explain right now, like in you will find suppose Fe biphenyl 3 actually, pyridine actually, you are finding 2 plus. In this complex, the charge transfer occurs from Fe2 plus to empty pi orbitals of Bpy ligand. That means the simplest example you take, suppose in case of you are finding FeCO whole 5, the CO means carbonyl groups, okay? And whereas in case of any NiCO whole 4, so here you can find there will be actually charge transfer from metal to ligand actually, okay? So therefore, the charge transfer absorption, you will find the movement of electrons between metal and ligand often 1,000 times stronger than the DD transition band. what you are observing, the charge transfer absorption you are finding. That's why you are finding so bright in color in case of the potassium dichromate, potassium chromate, KMnO4, like that. Here you are finding the ligand metal charge transfer of an electron from p orbital on a chloride, suppose U symmetry, to a metal's d orbital G symmetry. And metal to ligand transfer, you are finding transfer of electron from metal's d orbital to, as I have already explained, to pi orbital of carbonyl ligand, like this. Okay, so here you are finding like this, what we have already explained. Hello, this is understandable?
Sir, that one you said, na, the bright ones, will you explain that once more?
Yeah, what I'm trying to explain, suppose for example, the KMnO4, okay, and what we are saying the potassium dichromate, that is K2Cr2O7, then you are saying the potassium chromate, K2CrO4. Now look at here, in case of KMnO4, for example, what you are finding, that Mn plus 7. So naturally, there will be no D0 electron. So there is no question of DD transition, okay? And suppose in case of the potassium dichromate, K2Cr2O7, the chromium, the oxidation state is what? That you are finding plus 6, okay? So naturally, in this case also, you are finding the no electrons are present, isn't it? In the D atomic orbital. Is it clear? And similarly, you are finding in case of the K2CrO4, here also you are finding that in case of the chromium, basically what's the oxidation ovum state. So you are seeing that in this case, in case of the KMnO4, in case of K2Cr2O7, like this compound, you are finding there is no D electron. Okay, in case of the metal ion, as you are finding, they are having the higher oxidation state, Mn plus 7 and chromium plus 6. Now, then how they are showing the color? Because here it is, they are showing actually charge transfer, electron transfer. That means from ligand, in case of KMnO4, that means O2 minus charge. From here, the electrons actually are going to be attracted, charge transfer, by the vacant d atomic orbital, the central metal ion Mn plus 7, similarly in case of the chromium plus 6. And due to that, due to ligand to metal charge transfer, you are finding they are going to have high, means a very bright color also, like that, because as I have already shown you that this type of, just a minute, what I've shown,
Expected intensities, yeah, before
intensity
that.
almost more than almost 1,000 times actually. Rather
Yes.
than DD transition, you will find electron ligand electron metal electron transfer. It is almost going to be, you just see, that is for typical actually 10 to 1,000. For example, in case of the spin forbidden DD type of transition, you are finding epsilon, the absorbance actually. Okay, that is less than 1. And whereas you are finding the charge transfer fully allowed, you just see in case of the manganate ion, MnO4 2 minus. Look at here, it starts begin from 1,000 onwards, the epsilon value. So expected intensity of electric transition. So that's why you find so bright in color also. Is it clear?
Okay, sir. Sir, I have one question.
Yes, yes.
Sir, apart from this DD transition, we also have color changes in different other compounds, which are not coordinating compounds or complex compounds. That is because the theory means there also we have energy transfer, and that's why we have that.
For example, I'm telling you, suppose if you consider the zinc oxide, as we have already explained, in case of you are finding Zn2 plus, so what is happening? That it is all D10 electrons. Okay. So naturally, you are finding at the room temperature it is white in color, zinc oxide. But if you apply a heating effect, then you are finding that it is going to be little bit yellow in color. Then again, then when it comes to the room temperature, it is going to be actually then again the white in color. Okay, the remain colorless also. So why it is happening? They are actually due to, for example, I'm saying that again there is some electron transfer. How it is happening? This is actually some sort of the example of, you can say, the non-stoichiometric defect actually. Okay, non-stoichiometric defect where it is not proportionally happening because of the heating. There will be some non-stoichiometric, you can say, the metal excess defect or like that. Okay, is it clear?
Yes, sir.
Hmm.
Yes, sir.
Like that
Okay,
it
sir.
is. Hmm.
Hello, sir.
Sir, when will
Hello.
be our internal for chemistry?